Welcome to your lesson on creating quadratic models. Here's an example of a quadratic model. We have all these black data points, and those black data points, when you look at them, seem to follow this shape of a parabola. Therefore, a good model, and in mathematics a model is just an equation, a good model for these black data points would be a quadratic model, or a parabola. As we know, quadratic models are very important because all objects in our atmosphere follow parabolic paths, such as this one. Anytime we throw or kick an object, it follows this kind of path because of gravity. So to create a model for the path of any object in our atmosphere, we use quadratic models. Here's an example also of a ball that has been thrown following a parabolic path, which will require a quadratic model or quadratic equation to represent its path of motion. We also talked about suspension bridges, and many other objects that are designed in our world of engineering have this kind of shape. So this has a parabolic shape. Therefore, we had a quadratic model that represented that cable. So three main types of quadratic models or equations we've looked at are standard form quadratics, factored or intercept form quadratics, and vertex form quadratics. So we've worked with each of these in detail. Today you're going to look at how to make a model in each of these forms when you're given some data points that are on a parabola. Here's our first example. The x-intercepts of a parabola are x equals -1 and x equals 5. The parabola also passes through this point. So we know the x-intercepts and we know this point. So if you're thinking, well, which equation? We have these three different ways of representing parabolas. Which one would be the best for this? Well, the intercept or factored form would be best because we are actually given the two intercepts. So first thing we're going to do is look at this. And this is our general model. There's the a in front. That a is important. I'll show you in a minute why we need to have an a value there. We'll figure it out. So first of all, we rewrite the model by putting our two x-intercepts in there. So the -1 and 5 are here. Notice these signs have changed. And we know that because when we solve a quadratic, those two become the opposite of what they are, right? So -1 became a 1 and a 5 became a -5. So here's our model in intercept or factored form. However, we don't know the a value because there are many parabolas that have these two x-intercepts, but they can be of different widths, and the a value tells us how wide they are. So now to do that, we're going to take the point that we know, which is 4, -10, and we're going to substitute it in here as well. So the x value is 4, so both of those x's become 4. And the y value here is -10, so then we have -10 replacing the y. By doing this substitution of x and y, we're left with a as the only unknown, and we can solve this now for a. And then we will know the specific parabola with its a value that passes through this point. So solving that, 4 plus 1 is 5, 4 minus 5 is -1, and we have this here, -5a. Divide both sides by -5, and a is 2. So now we know a. So we know that there's many parabolas, actually infinite parabolas, that pass through these two x-intercepts, but this specific one with an a value of 2 also passes through that point for -10. Let's take a look at that on Desmos, because I'm wondering, why wouldn't this be an okay model? Because this model has x-intercepts of -1 and 5, so let's check. So let's go to Desmos, y equals ax plus 1, x minus 5. Is that right? Yeah. So notice here are two x-intercepts, -1 and 5. So that's what we were just talking about. But right now the a value is 1. So watch as I change the a. What happens to this? This parabola will remain locked in these two x-intercepts, but the width will change. See, the parabola is changing, but the two x-intercepts remain locked. Again, keep your eye on those 2 points. They remain like anchors. All right, see, the parabola changes. And we found out for our parabola, the a value had to be 2, right? So I'm going to make a 2 right now. Here's an a value of 2. So those are two x-intercepts again. And our parabola in that problem, when a value was 2, it passed through the point 4, -10. So let's check. Where's 4, -10? Here is 4, and here is -10. So there's that point, 4, -10. There it is. You can see the point right there, 4, -10. If I change the a value, the parabola would no longer pass through that point. So that's why the a value is important, because there are infinite parabolas that have those x-intercepts, but only one of those infinite parabolas also passes through that. Okay, so let's look at the next one. Here we have another parabola. We're given information. The vertex is this, and it passes through this point. So this time we're given the vertex. So what form of a parabola should we begin with? Well, we should begin with vertex form. So here's vertex form, and we begin with vertex form because we were given the vertex. So first we plug in the vertex, and as you remember, the x value of the vertex goes here, and it is always the opposite sign. So I see -2, it's +2, and the y value of the vertex always goes here. So this is x value, this is y value. So I've rewritten the parabola now with that vertex. Again, just like the last one, the a value is important because there are infinite parabolas with this vertex, but they have different widths as you change the a. So now to figure out what the a value for this specific parabola, because this parabola must pass through this point, we're going to plug that point in. So y value of 28 goes here, x value of 2 goes in here for x. And now we have, again, a is our only unknown, so we can solve for a. This is 2 plus 2 squared is 4. Sorry, 2 plus 2 is 4. Is this correct? What's going on here? 2 plus 2 is 4. 4 squared is 16. There we go. 16 minus 4. 16a minus 4. Now we're going to add 4 here. 32 divided by 16. A is 2. So now we know our specific parabola that has this vertex and passes through this point is this parabola. A must be 2. Again, we could look at Desmos for a moment to see what's going on there. So let's check. Y equals ax minus 2. It was minus 2, right? No, it's plus 2. And this was minus 4. Okay, so there's that parabola. That parabola, has a vertex of -2, -4. A is currently 1. If we change the a value, look, the vertex is locked. Because we have it in vertex form, and that vertex is locked. It cannot change. But the parabola itself changes. And now we're looking for the parabola that passes through, it was what point? 228. So I'm going to put 228 in here. 228. And label that point. Let's see where the point is. There it is. It's all the way up there. This parabola will only pass through that point when a is, we just found out a must be 2. So let's make this 2. There, a is 2. And now you can see, look, it passes right through that point. When the a value is any other value, we still have the same vertex, but it doesn't pass through that point. So there's only one of the infinite parabolas that passes through that point, and it is when a is 2. All right, so that's the introduction. So try this. Try the same approach for this one. Okay, now check your work. So here we were given x-intercepts. So again, we begin with intercept or factored form. We plug in our 2 intercept values, make them the opposite signs, substitute the point we're given, y and x here, use that to solve for a. Here's 5 times -1, and that gives us a value of -3. And then put that a value back in this parabola here, because now we know we have this specific parabola with these 2 x-intercepts, but the a value must be this in order for it to pass through here. Again, you can check in Desmos. If you put this parabola in, you would notice it has these 2 x-intercepts, and it would pass through this point. Change that a value, and it would no longer pass through that point. Okay, try one more. In this one, we notice we were given the vertex, therefore begin in vertex form. Substitute the vertex. That 5 is -5 here, that 1 is a +1 here. Now we know there are infinite parabolas that have that vertex, but there's only one that passes through this point. So we're going to plug in our y and our x values. Y becomes 17, x becomes 7. Now we can solve for the a value, which will create the exact parabola that has this vertex and passes through this point. Solve that. A is 4. So there is the single parabola that has that vertex and passes through that point. Again, change the a value. We'll still have the same vertex, but the parabola will no longer pass through that specific point. All right, here's another one. This is more word problem style for this one. Okay, hope you noticed that this one also we were given the vertex, because it says a ball is thrown. After 2 seconds, the ball reaches a maximum height. So imagine a parabola going up and over like that. There's a maximum point. The maximum point is our vertex. So we're given a vertex here. If we're given a vertex, we can go to vertex form. We're also given more information here. It lands on the ground, so the ball lands on the ground 5 seconds later. So that is an x-intercept with an x value of 5 and a y value of 0 because it's now on the ground. So we're given a vertex and another point. Here's our vertex form. There's the vertex going into it right here. Here is that given point going into it, 0 and 5 here. Solving this for a is -1. Therefore, the single parabola that can explain or model this situation is this parabola right here. A is -1. Again, if a changed, it would no longer pass through that single point that we're looking for. All right, here's another one. Now instead of being given information in words, you're given information as a parabola. So look at, what do you have? What do you know about this parabola? Okay, hopefully you spotted its vertex form because you know the vertex. So you know the vertex and you know some other point. So again, we begin vertex form, put in the vertex, these two values. Also, in one step, I have substituted the point we're given into the x and y. So the x and y here have been replaced with the values, x and y values of that. You solve that for a, it's -2. And then we know that this is the parabola model for this in vertex form. Another graphical one, look at this one. What are you given on this one? Look carefully. This time we were given two x-intercepts right here and right here. This is not a vertex. The vertex is here. We don't know it. This is another point though. So we can use intercept form or factored form. Our two x-intercepts are -3 and 2, which becomes 3 and -2. Then I've also in the same step substituted this point, which is 0, 3. So here's 0 for x, 3 for y. That allows us to solve for a, which is -1/2, and that allows us to give the entire model for this parabola. Remember that you're not locked in this form. You can multiply all this out and change this back to standard form. Then from that standard form, you can complete the square to get to vertex form if you'd like. All right, one last thing. This is a challenge problem. Maybe you've noticed that we've been doing all kinds of stuff except for standard form. So let me go back to the beginning here. There are 3 forms here. We've been concentrating on this one, but we haven't looked at standard form yet. That's because standard form ones are usually the toughest ones to make a model for, and you'll see why. Okay, so here's one. It says, let's say we have this parabola, and we're given the c value in this case, but we don't know these a and b values here. This is standard form. We know it passes through these 2 points. First, it says, step 1. Well, we know 1 point, so why don't we take that 1 point and substitute into the equation? So here's our parabola. I'm going to put in that point -1, 1 in there. So 1 is the y value, -1 is the x value, so -1, -1, the x's. That can be simplified a little bit into 1 and then a minus b minus 4. So we've created an equation with 2 variables. You may remember doing this when we did modeling of a bouncing ball. That activity had us doing this as well. So now we're going to take the other point that was given to us and substitute that into the equation of the parabola as well. So there's the parabola equation. Into that, we're going to put in the point 2, -2. So that means y is -2, x is 2. Simplify that equation into this. Now we have 2 equations with 2 variables. That means we can use substitution to solve. So the hint here is, let's use simultaneous equations to solve. Here's one equation, here's the other that we just created. These ones, if we want to use elimination, maybe we can make these be both of them 2. So I'm going to take the first equation, multiply everything by 2, it becomes this. The second equation, I'm going to leave unchanged. Now, if I combine these 2 equations, this -2b and +2b will cancel. And I add those cancel, all these add up. And if you remember how to do elimination, now we have this. That allows us to solve for a, which then allows us to solve for b, because we can substitute that back in and get b. So we have found a and b. Now we know the equation of this parabola, because we know what the a and b values are, and we have the whole equation. So this was actually an easier example of this. Sometimes we don't know the last point here. For example, I gave you one like this last week or 2 weeks ago. You know 3 points, you know standard form, you don't know any of these values, a, b, or c, and then there was all this work. We created the equation for using each point. So I'm going to put this all here because I'm running out of time in my video, but this is a reminder of something we did a few weeks ago. All right, take a look at that, remind yourself how you plug in 3 times, and